In 1938, a physicist at Columbia University proved that atomic nuclei could absorb and release radio waves at a precise, predictable frequency when placed inside a magnetic field. Nobody thought it had anything to do with the human body. 33 years later, someone asked what would happen if it did. Isidore Rabi wasn't looking for a medical tool. Firing beams of atoms through magnetic fields and tuning radio waves until the nuclei absorbed them. That was his method, and it was extraordinary in its precision. Rabi won the Nobel Prize in Physics in 1944. Then, working separately, Felix Bloch at Stanford and Edward Purcell at Harvard took the phenomenon somewhere Rabi hadn't gone. Nuclear magnetic resonance didn't only work on atomic beams in a vacuum. Ordinary matter responded to liquids, solids, any substance containing hydrogen. Bloch and Purcell shared the Nobel in Physics in 1952. For 2 decades after that, the technique lived quietly inside chemistry labs, used to identify molecules and probe the structure of compounds. Nobody brought it near a living person. Raymond Damadian was the physician who changed that. Not a physicist, not a chemist, a doctor who wanted to know if MMR could tell him something clinical. Damadian's 1971 paper in Science showed that cancerous tissue responded differently to nuclear magnetic resonance than healthy tissue. The relaxation times of the signals were measurably and consistently distinct. His conclusion was precise. The technique might prove useful for detecting malignant tumors inside the body. Most physicists moved past it. Paul Lauterbur didn't. 2 years after Damadian's paper, Lauterbur realized that if you deliberately varied the magnetic field strength across space, gradient fields, each point inside the body would emit its signal at a slightly different frequency. Location would encode into frequency, and frequency could be decoded into a map. Published in Nature in 1973, the paper was nearly rejected because the proof of concept images weren't good enough. They changed their minds. That decision made it one of the most consequential documents in the history of medicine. Meanwhile, at the University of Nottingham, Peter Mansfield was solving the problem nobody had fully confronted: speed. Mansfield's technique, echo-planar imaging, cut scan acquisition times from tens of minutes to fractions of a second. Fast enough, eventually, to image a beating heart. Now all 3 men were racing: Damadian, Lauterbur, Mansfield, each convinced the others had gotten the important parts wrong. In 1977, working with a small team and a machine he built himself and named Indomitable, Damadian completed the first full-body scan of a living human being. Competition between them grew personal, and the bitterness held. Lauterbur and Mansfield received the Nobel Prize in Physiology or Medicine in 2003. He was left out. Purchasing full-page advertisements in the New York Times, the Washington Post, and the Los Angeles Times, he ran a campaign headlined, "The Shameful Wrong That Must Be Righted." Nobel statutes allow up to 3 recipients. Damadian could have been included without displacing either winner. Stockholm has never publicly explained the exclusion. Building the machine itself turned out to be a problem several times harder than proving the concept. Hydrogen protons are the nuclei you're interrogating, the most abundant atom in the human body, but extraordinarily quiet relative to the electromagnetic noise surrounding them. Signal strength scales with field strength. A standard clinical MRI runs at 1.5 to 3 Tesla, roughly 30,000 to 60,000 times stronger than Earth's magnetic field, and that field has to be uniform to within a few parts per million across the full imaging volume, or the image distorts beyond use. Generating a field that powerful and stable requires superconducting coils, wire carrying enormous current with 0 electrical resistance. Superconductivity doesn't happen at room temperature. Those coils must be cooled with liquid helium to approximately 4 Kelvin, minus 269 degrees Celsius, 4 degrees above absolute zero. Shimming coils then fine-tune the field, compensating for every remaining deviation from uniformity. All of it has to remain stable across a scan that might run 40 minutes or more. Fail any single component and there's no degraded scan. Nothing. Here's the part that lands strangely. All of that infrastructure, the liquid helium, the months of calibration, the millions of dollars of hardware, produces a machine that is completely harmless to the tissue it examines. No X-rays, no ionizing radiation. Pregnant patients can be scanned without risk. That same patient can come back the next day, and the day after that, with 0 cumulative biological cost. But the magnet doesn't care about biology. Steel does. Michael Colombini was 6 years old and being scanned at Westchester Medical Center in New York in 2001 when a hospital worker brought a portable steel oxygen tank into the MRI room. Pulled toward the magnet, the tank struck the child in the head. Michael died that day. MRI magnets of this type don't switch off between patients. They run continuously, always exerting their pull on anything ferromagnetic within range, invisible and patient. Rebuilding this technology from nothing requires 4 separate bodies of knowledge that barely coexisted in the same room before the 1970s. Nuclear physics to understand the signal being generated. Cryogenics to sustain the temperature the magnet requires. Precision superconductor manufacturing to carry current without quenching. Computational mathematics to convert raw frequency data into a picture a radiologist can read. Remove any one of those and the system doesn't produce a degraded image. Go. What gets assembled when all four come together is 60 years of compacted scientific effort across disciplines that had to be invented largely in parallel with each other. Rabi measured the resonance of a nucleus in a Columbia lab. Bloch and Purcell showed that resonance existed in ordinary matter. Damadian asked what a doctor could learn from it. Lauterbur turned it into a map. Mansfield made the map fast enough to use. And then, somewhere, someone lay inside a narrow tube and held perfectly still, while the same physics that makes a compass needle point north reached directly inside their living brain, without a blade, without a beam, without touching a single cell.